Data storage and big data management architecture play a vital role in machine learning due to the following reasons. Data availability. Machine learning relies on large datasets. Efficient storage ensures the availability of quality data for model training, testing, and validation. Scalability. Big data management systems handle vast and growing datasets seamlessly, supporting the scaling needs of machine learning projects. Data integration. Architecture enables the integration of diverse data sources, improving the dataset's richness and model accuracy. Performance. Optimized storage and retrieval reduce latency during data preprocessing and training. Security and compliance. Proper architecture ensures data security and adherence to regulations like GDPR, critical for sensitive information. Cost optimization. Structured storage minimizes redundancy and reduces resource costs, making projects sustainable. Big data architecture is integral to machine learning, enabling efficient processing and analysis of massive datasets. Here are key ways it supports machine learning. Data storage and management. Big data architecture offers scalable, distributed storage solutions like Hadoop distributed file system and cloud-based systems. These solutions manage structured, semi-structured, and unstructured data from diverse sources such as sensors, social media, and logs. Machine learning algorithms can access the stored data for training and inference. Data ingestion and pre-processing. Big data architectures facilitate the ingestion of large data volumes from multiple sources. They support pre-processing tasks, including cleaning, transformation, and feature engineering, using distributed frameworks like Apache Spark. These steps are vital to prepare data for machine learning models. Distributed computing and parallel processing. Frameworks such as Apache Hadoop and Apache Spark enable distributed computing, allowing data to be processed in parallel across clusters. This capability accelerates machine learning tasks like training and inference on massive datasets, reducing processing time compared to single machine setups. Scalability and elasticity. Big data architectures are designed for horizontal scaling, allowing clusters to grow as data volumes or processing needs increase. Cloud-based platforms enhance the scalability with elasticity, enabling dynamic allocation and deallocation of resources to optimize cost and performance for machine learning workloads. Distributed machine learning. These architectures support distributed machine learning frameworks, including TensorFlow, PyTorch, etc., enabling the training and deployment of models across clusters. By distributing the workload, they facilitate efficient training on large-scale datasets. Real-time analytics. Big data architectures integrate streaming data processing frameworks like Apache Kafka. This allows organizations to feed streaming data into machine learning for near real-time predictions. Data ingestion involves capturing and importing data from multiple sources, such as databases, IoT devices, and social media platforms. Tools like Apache Kafka, Flume, Logstash, and NiFi are commonly used for this purpose, ensuring seamless and efficient data collection. Data storage focuses on storing structured, semi-structured, and unstructured data using distributed systems. Popular solutions include HDFS, Amazon S3, Google Cloud Storage, and Azure Blob Storage, which provide scalability and reliability for big data needs. Data processing involves transforming and analyzing data through batch or real-time methods. Frameworks like Apache Spark, Hadoop MapReduce, and Apache Flink enable efficient handling of large-scale data to support analytics and machine learning tasks. ETL, extract, transform, load operations are essential for preparing data by extracting it from sources, transforming it into usable formats, and loading it into target systems. Tools like Informatica, Talend, AWS Glue, and Apache NiFi streamline this process. Data integration ensures a unified view of data by combining it from diverse sources. Solutions like Apache Camel, MuleSoft, and Talend Data Integration facilitate smooth integration workflows to enrich datasets for analysis. Data analytics involves performing advanced analysis, statistical computations, and visualizations. Tools like Tableau, Power BI, Apache Zeppelin, and Jupyter Notebooks are widely used to derive insights from data. Search capabilities enable fast querying and indexing of data, crucial for large datasets. Elasticsearch, Solr, and Amazon OpenSearch are common tools that provide high-speed search and retrieval. Machine learning is supported by frameworks like TensorFlow, PyTorch, Apache Mahout, and H2OI, which facilitate model training, deployment, and inference on big data platforms. Scalability is critical for managing growing data volumes and computational needs. Technologies like Kubernetes, Docker Swarm, Amazon EC2 autoscaling, and Google Kubernetes Engine ensure dynamic resource allocation. Security and governance ensure data privacy, access control, and compliance with regulations like GDPR. Tools like Apache Ranger, Apache Knox, AWS IAM, and Azure Active Directory help safeguard data in big data platforms. Workflow orchestration manages and schedules data pipelines and workflows. Solutions such as Apache Airflow, Luigi, and Oozie enable automation and efficient task management. Metadata management maintains information about data, including its source, structure, and processing history. Apache Atlas, Alation, and Informatica EDC are examples of tools that provide robust metadata solutions. Monitoring and management involve tracking system performance, resource usage, and application health. Tools like Prometheus, Grafana, Nagios, and Splunk ensure smooth operations and timely issue resolution. Apache Big Data Architecture encompasses several key components to handle the entire lifecycle of big data, from ingestion to analysis. Data ingestion tools like Apache Kafka and Flume collect data from diverse sources such as IoT devices and social media. Storage systems like HDFS and Apache Cassandra provide scalable and distributed storage for structured, semi-structured, and unstructured data. Processing frameworks like Apache Spark and Hadoop MapReduce enable batch and real-time data transformations. For data integration, tools like Apache NiFi unify data from various origins, ensuring consistency and accessibility. Metadata management is achieved with Apache Atlas, which tracks data lineage and governance. At a high level, Apache Big Data Architecture integrates these components into a unified pipeline. Data flows in through ingestion systems and is stored in distributed storage layers for durability and accessibility. It is then processed using scalable computing frameworks that support both real-time and batch operations. Workflow orchestration tools like Apache Airflow manage pipelines, while analytics and machine learning frameworks like Apache Mahout and Spark MLib extract insights and predictions. Security is maintained with tools like Apache Ranger, ensuring compliance and data protection. This modular and scalable architecture supports complex big data workloads across industries. AWS Big Data Architecture integrates a variety of services to handle data ingestion, storage, processing, analytics, and security at scale. Data ingestion is managed using services like Amazon Kinesis and AWS Data Pipeline, which can handle real-time and batch data from diverse sources. Storage is facilitated through Amazon S3 for scalable object storage, Amazon Redshift for data warehousing, and DynamoDB for NoSQL data. Processing is powered by AWS Glue for ETL, Amazon EMR for distributed big data frameworks like Hadoop and Spark, and AWS Lambda for serverless real-time processing. At a high level, AWS Big Data Architecture involves data flowing through ingestion layers like Kinesis streams into storage solutions such as S3 or Redshift. These storage systems feed into processing services like EMR or Glue for transformations and analytics. Insights are generated using Amazon Athena for querying, QuickSight for visualization, or SageMaker for machine learning. Security and compliance are maintained through AWS IAM for access control, KMS for encryption, and Macie for data privacy monitoring. This architecture is modular, allowing enterprises to scale resources dynamically and efficiently handle complex data workloads. Azure Big Data Architecture provides a comprehensive ecosystem for managing data ingestion, storage, processing, and analytics. Data ingestion is handled through Azure Data Factory for batch ETL processes and Azure Event Hubs or IoT Hub for real-time streaming data. Storage options include Azure Data Lake for scalable data lakes, Azure Blob Storage for unstructured data, and Azure SQL Database or Cosmos DB for structured and NoSQL data. Processing is powered by Azure Synapse Analytics for big data analytics, Azure Databricks for Spark-based workflows, and Azure Functions for serverless processing. At a high level, Azure Big Data Architecture organizes data flow from ingestion layers like Event Hubs or Data Factory into storage solutions such as Data Lake or Blob Storage. These storage layers support data processing and transformation using Synapse Analytics or Databricks. Insights are derived through tools like Azure Machine Learning for predictive analytics and Power BI for interactive visualizations. Security is integrated throughout the architecture with Azure Active Directory for identity management, Azure Security Center for monitoring, and compliance features for regulatory adherence. This scalable and cloud-native architecture is optimized for diverse big data workloads. Google Big Data Architecture is built on Google Cloud Platform, GCP, offering a comprehensive suite of services for ingestion, storage, processing, and analysis. Data ingestion is managed through tools like Cloud Pub/Sub for real-time messaging and Cloud Dataflow for batch and stream processing. Storage solutions include BigQuery for data warehousing, Cloud Storage for unstructured data, and Firestore or Bigtable for NoSQL databases. Processing is supported by tools like Dataflow for ETL and batch jobs, Dataproc for running Hadoop and Spark clusters, and Vertex AI for machine learning workflows. At a high level, Google Big Data Architecture orchestrates data flow from ingestion services like Pub/Sub into storage solutions such as BigQuery or Cloud Storage. These layers feed into processing tools like Dataflow or Dataproc for data transformation and analytics. Insights are derived through BigQuery for querying, Looker for visualization, and Vertex AI for advanced machine learning. Security is embedded throughout the architecture using Identity and Access Management, IAM, Cloud Key Management, and compliance certifications. This flexible and scalable architecture supports real-time and batch data processing for a variety of big data applications. Stream processing in data science and machine learning. Stream processing is essential in data science and machine learning, enabling real-time analysis, continuous data handling, and adaptive model updates. Here's why it matters. Real-time analysis. Stream processing facilitates immediate data analysis as it arrives, unlike batch processing, which waits for data accumulation, often causing delays. This supports timely decision-making and swift responses to dynamic conditions. A continuous data handling. Many applications demand uninterrupted data processing. Stream processing frameworks efficiently manage unbounded data streams for tasks like fraud detection, real-time monitoring, and recommendations. A dynamic model updates. Changing data distributions can reduce model effectiveness over time. Stream processing supports continuous model retraining and adaptation, ensuring accuracy in evolving environments. Scalability and efficiency. Designed for high-volume, fast-paced data streams, stream processing frameworks enable parallel processing, distributed computing, and optimized resource use, supporting massive workloads efficiently. Or event-driven architectures. Stream processing integrates with event-driven systems, triggering data analysis in response to events. This allows leveraging diverse data sources for real-time analytics and decisions. A high-velocity data handling. Domains like social media, IoT, and financial markets generate rapid data streams. Stream processing enables real-time ingestion and analysis, delivering insights without relying on batch storage. Popular stream processing tools for machine learning. Here are some widely used tools and platforms for stream processing in machine learning. Apache Kafka, a distributed platform for handling real-time data streams. It offers high-speed data transfer, fault tolerance, and storage. Kafka integrates well with ML frameworks, making it ideal for real-time data ingestion for training and predictions. Apache Flink, an open-source tool for both batch and stream processing. It handles events with low latency, manages state, and is fault-tolerant. Flink supports machine learning workflows by connecting with ML libraries. Apache Spark Streaming, part of the Apache Spark ecosystem. This tool processes live data streams and works with other Spark components like SQL and mlib. It enables seamless stream processing and machine learning in a single workflow. Amazon Kinesis, a managed streaming service by AWS. It helps collect, process, and analyze real-time data at scale. Its components, like Kinesis data streams and analytics, support end-to-end machine learning applications. A Google Cloud Dataflow, a Google Cloud service for creating stream and batch processing pipelines. Built on Apache Beam, it integrates with tools like BigQuery and TensorFlow, making it easy to develop ML workflows. Apache Storm, a real-time system for processing streaming data with low latency. The choice of tool or platform depends on factors such as scalability, fault tolerance, integration with existing systems, and the specific needs of the machine learning application at hand. Overall, stream processing empowers data scientists and machine learning practitioners to work with real-time data streams, continuously process and analyze data, adapt models to changing conditions, and build scalable and efficient data-driven applications. It enhances the agility and responsiveness of data science and machine learning workflows, enabling organizations to derive actionable insights and drive intelligent decision-making in real time. These are various algorithms and data structures commonly used in the field of computer science, specifically in data streaming and probabilistic data structures. Let's briefly discuss some of them. Bloom filter. A Bloom filter is a space-efficient probabilistic data structure used to test whether an element is a member of a set. It provides a fast and memory-efficient way to perform set membership queries, but it may produce false positives, indicating that an element is in the set when it is not, due to its probabilistic nature. Sketch algorithms. Sketch algorithms, also known as streaming algorithms or approximation algorithms, are designed to process data in a streaming fashion, where the entire dataset is not available at once. These algorithms aim to summarize or approximate the data using limited memory and computational resources. A count-min sketch. The count-min sketch is a probabilistic data structure used to estimate the frequency of elements in a data stream. It provides an approximate count of each element, even in the presence of large datasets and limited memory resources. The trade-off is that it may produce overestimations. A distinct value sketch. The distinct value sketch is another probabilistic data structure that estimates the number of distinct elements in a data stream. It provides an approximate count of distinct elements using limited memory resources and is particularly useful for counting distinct elements in massive datasets. A reservoir sampling. Reservoir sampling is a technique used to obtain a random sample of a fixed size from a larger data stream or dataset. It ensures that each item has an equal chance of being selected, regardless of the size of the data. This is useful when the entire dataset cannot be stored in memory, but a representative sample is required. Decay window. A decay window, also known as a sliding window or exponential decay window, is a time-based technique used to give more weight to recent data and gradually decrease the significance of older data in a streaming or time series scenario. It is commonly used for tracking trends or summarizing time-varying data. These algorithms and data structures are primarily related to the field of data streaming, where data arrives continuously and needs to be processed efficiently using limited resources.